Alright, let us learn about quantization of light. Alright, okay, so before this, in previous chapter, in geometrical optics and physical optics, you are learning the light behave as wave. For example, in geometrical optics, you learn that light can be reflected and refracted, isn't it? You learn that the light can be reflected, okay, can be refracted, okay, and then in physical optics, you learn that light can undergo interference, and then we have also diffraction. All these four characteristics, reflected, reflection, refraction, interference, and diffractions, they all prove that light behave as wave. Okay, behave as wave. So, but do you know that in modern physics, the light also behave as particle, not just wave. It behave as like particle. Okay, for example, like you see this is the fiber optics. This fiber optics is actually a very good example to describe photon. To describe the light seems like particle rather than wave. Wave is something like we know something like this lah. This is the wave. Okay, but particle, it exists in particle form. Can you imagine the light in particle form? Yeah. So you see, this is the light, going. So also all these are particles of light. Particles of light. So these particles carry energy. So is light a wave or is it a particle? Actually, light can behave as both properties. In previous chapter, geometric optics, physical optics, you learn that they have all the wave properties, but now light also behave like particle. Okay, in the following experiment, what we call the photoelectric effect, photoelectric effect experiment. This photoelectric effect experiment carried out by Einstein prove that light also behave like particle. Okay, instead of just like wave. So we're going to particle. It is shown in this experiment. Okay, it is shown in the photoelectric effect experiment. Okay, photoelectric effect experiment. Okay. So you see this light, just like particle. You see there are many particles in the light. So I have a simulation to show you. Okay, this is the simulation. Okay, before that you need to know light has behave as photon particles. Okay, what is actually photon? Okay, let us look at what is actually photon first. Photon is actually called the one particle of light. A small particle. Actually, here the light is not just the visible light. This photon is actually one particle of the electromagnetic radiation. That's actually the more proper terms. Yeah, photon is actually one particle of electromagnetic wave or electromagnetic radiation. What type of electromagnetic radiation we have? Yeah, or actually this light here is not just the visible light we see. This light here actually is the electromagnetic radiation. So what type of electromagnetic radiation we have? We have, for example, we have like radio wave. We have radio wave. We have infrared. We have ultraviolet. We have X-ray, and also the gamma ray, and also the visible light, isn't it? Visible light. So all these are actually considered electromagnetic radiation. So what is actually photon? photon is just one particle inside the electromagnetic radiation. So we have photon of radio wave, we have photon of infrared, photon of ultraviolet, we have photon of X-ray, we have photon of gamma, and also photon of visible light. So all these radiation, they have their own photons because they have different frequency and different wavelength. Okay, we will go into that. So photon is actually one particle of electromagnetic radiation. Okay, so one particle is like this one lah. You see, this is actually the light. Yeah, the light beam. Okay, the whole thing is the light beam. Whole thing is a light beam, but each one of them is the photon. Each particle of it is a photon. So we can say photon is like the basic building block, the basic block of the light beam. Okay, so a light beam has many photons. So for example, okay, we will talk about that later. So first of all, photon is the smallest particle of light. One particle of light. It has no mass at all, zero mass, but it has a lot of energy. Okay, this photon contains one quantum of energy. One quantum of energy. How much is the energy? We will learn in the Planck's quantum theory to calculate the energy of one photon, which is E equal to hf. We will learn about that later. So photon is a one quantum of energy. What is mean by one quantum? Quantum means the packet of energy. A packet of energy, a bundle of energy, which is equal amount in every photon. Yeah, what I can say is what is quantum? Maybe I can describe over here. So for example, let's say one quantum is how much energy? Maybe the one quantum of energy is maybe 10 joule. Yeah, 10 joule is actually a lot. Okay, one quantum is actually a lot. So we can say this is energy for one photon. Yeah, this energy for one photon. So we can say that this is the light, the whole light beam. So each photon carries how much energy? Each photon carries how much energy? One quantum of energy. One quantum means each of them has same amount of energy. 10 joule, 10 joule, 10 joule, 10 joule. Yeah. This is 10 joule, 10 joule, 10, 10. None of them has more energy than the other. They have all equal amount. Yeah. One quantum means that means every photon. Yeah. We can say every photon, same energy. Every photon same energy, 10 joule. And it is the smallest amount. One quantum of energy actually is the smallest amount of energy the light beam can have. Yeah, smallest amount of energy. So in the light, you can only see energy with 10. The smallest amount of this light is only 10 joule. 20 joule. Later on is 20 joule, 30 joule, and they have the equal amount. It's just like a staircase, you know. It's just like a staircase with this you know, equal height. All of them equal height. All of them equal height. Yeah. So we can say all of them have the smallest amount of energy you can find in that light is 10 joule. Later on is the light you can have 20 joule, 30 joule, and 40 joule, and so on. Yeah, the smallest amount of the energy is one quantum, which is 10 joule, for example. Okay, so you cannot find the light with energy 15 joule. Impossible. If the one quantum is 10 joule, you cannot find energy light with 15 joule. You can only find the light. You can only find the light with 10 joule, 20 joule, 30 joule, 40 joule. That means it is like n multiply 1 quantum, n multiply 1 photon, and the numbers of photon multiply the energy for 1 photon. Okay, energy for 1 photon or 1 quantum. Okay, so it depends on how many photons you have. Like this one, you have like this example, you have 6 photon. Okay, here you have 6 photons of light. 6 photons of light. So this light beam has how much energy? It has 60 joule of I can write like this. It has 6 times photon. 1 photon is 10 joule. Okay, 1 photon is 10 joule. So it has 60 joule of energy. This is the energy of this light. This is the energy of this light. It has 60 joule of energy. Okay, and each photon you have equal amount of energy. You won't find any photon with only 5 joule. No, you won't find any photon with 7 joule. No, if one quantum is 10 joule, then all of them is 10 joule. Each of them has energy 10 joule. You won't find any photon with 7 joule or 5 joule. No, all of them have the same 1 quantum of energy, which is the smallest amount of energy, 10 joule. All of them 10 joule. Yeah. So the energy of light, you can have maybe 10 joule or 20 joule, 30 or 40 joule. Depends on the number of photon. Yeah, number of photon. So it's n times photons. Okay, what is the formula to calculate this energy of 1 photon more accurately? We will learn about that. Yeah. So quantum is a packet of energy. It's just a packet of energy with fixed amount for every photon. And this photon travel at the speed of light. Because we know that all these electromagnetic radiation, they have the same speed. Which is all of them have the same speed, which is 3 exponent 8 meter per second. They have the same speed, very fast. The speed of light. We can say this is speed of light. So this photon also travel at the speed of light in vacuum. 3 exponent 8. This is the speed of the electromagnetic radiation. As I said, photon is not just for visible light. Photon is not just for the visible light that we can see, the red light, the violet light, the blue light. It's not just for the light with color. The photon is also particles for other electromagnetic radiation like radio wave, infrared, UV, gamma, X-ray. So we have photon for X-ray, we have photon for gamma ray, we have photon for radio wave also. Okay, and all these light, all these electromagnetic radiation, radio wave, X-ray, gamma ray, all of them have photons. All of them behave like particle also. All of them behave like particle. And how to prove that they behave like particle? We have one experiment to prove it. Photoelectric effect experiment. Okay, that's good. Now let's look at the Planck's quantum theory. So how to actually calculate this energy of 1 photon? Just now what I give is just example, 10 joule. I just give a value 10 joule. But how to calculate this energy of 1 photon? Yeah, 1 quantum means the energy for 1 photon. It is the 1 quantum is the energy for One quantum is energy for one photon. Yeah? As I said, photon, it has one quantum of energy. It has one quantum of energy. So one quantum is actually energy for one photon. Alright? So how to calculate this energy of one photon, or we can say energy of one quantum? Energy of one quantum. How to calculate? We have a formula. This photon energy or quantum energy, it depends on the wavelength of light or frequency of light. This is the most important thing in Planck's quantum theory. Okay, let us first look at what is explained in Planck's quantum theory. Okay, shall we? Okay, before that, I haven't shown you this simulation that light behave like photon particles. Here I have a simulation to show you. Yeah, as I want to say, light behave like particle, isn't it? Light behave like particle. Yeah, light behave like particle. So I have a simulation to show you. Here is one picture about the fiber optic. It looks like, it looks like light behave. It looks like light looks like a particle. Okay, but here there's one interesting simulation to show you. Yeah. You see, this is the incident light. You see, this is actually the orange light. We use the orange light with intensity 100%. So let's look at the orange light. Do you see the light particle? Yeah, they have the, you see, they have the wavelength. This is the wavelength. This is the particle. The blue one is actually the electron ejected from the metal surface. Don't care about the electron first. Yeah, we just want to look at the orange particle. You see, this orange particle is raining on this metal surface. Then electron is ejected. Yeah. So you see, light also behave like. Light also looks like particle. Light also looks like particle. Yeah, it's like raining. Yeah, raindrops. Okay. Now let's look at this one. Yeah. Now what is described by Planck's quantum theory? What is described by Planck's quantum theory? So let's look at this. Assumptions made by Planck in his theory are the electromagnetic radiation by the black body is not in a continuous stream of wave, but in a discrete little bundles, separate packets of energy called quanta or quantum. Quanta means plural, quantum is singular, known as photon. This means the energy of electromagnetic radiation is quantized. Not all values of energy is possible. So what I'm saying is, what is here is saying is the radiation, the light, is actually what I'm explained over here lah. Yeah, the light exists in discrete form. Yeah, in it has the energy is quantized. Not all values. You see that here? Not all values of energy is possible. So you cannot find energy with 15 joule or maybe 17 joule of light. Yeah, the energy of light only exists in 10 joule, 20 joule, 30 joule, 40 joule if the one photon of energy is 10 joule. You cannot find energy with 15 joule, 17 joule. No. Yeah, energy is not continuous. The value is not continuous. Yeah, the value is discrete. Like a step. You see, discrete is the it's not like a slide, you know. It's the energy is not like a slide. Energy of light does not exist in a continuous form. No. Yeah, that means you can it's not like energy of light. You have maybe 2 joule, 5 joule, 17 joule, all value you have even 17.5 joule, 18.89 joule. It's not like that. It's not continuous. It's discrete. Yeah, this is what you call discrete lah. Yeah, it's not continuous form. It's like discrete form, like a staircase. Okay. Not all values of energy are possible. Yeah, it's quantized with a okay, discrete value. Okay, so energy of radiation depends on frequency. Depends on frequency, or depends on wavelength. What is mean by frequency? Frequency is actually the type of light, or we can say frequency here is it can be described in terms of wavelength. Okay, let us look at this one, the slide here. Yeah. So why you say energy of the radiation, energy size? This means the energy of the photon lah. Energy of the photon depends on frequency, which is this formula E equal to hf. So energy of one photon depends on frequency. So just now, how to calculate the energy of one photon? Yeah, how to calculate energy for one photon? This is the formula. Energy of one photon depend on frequency. So frequency you can also write as C over lambda. So what is actually why frequency can change to lambda? Because we have the formula, this speed of light is equal to f lambda, isn't it? Speed of light equal to f lambda. So f is equal to c over lambda. C over lambda. So you just substitute the f with c over lambda, and you got this hc over lambda. Hc over lambda. So now h is called the Planck's constant, 6.63 exponent negative 34 joule second. This one is given in the list of constant. Yeah, list of constant. Okay, I want you to see the unit. Yeah, I want you to see the unit. You see this Planck's constant, the unit is in joule second. You see that? Joule second. You see? Joule second. So okay, so your unit for the Planck's constant is joule second. Joule second. Okay, Planck's constant is joule second. Frequency is 1 over period, isn't it? Frequency is actually per second. The unit is per second. Frequency is per second, because it's like frequency is, you learned before, frequency is 1 over period, isn't it? 1 over period. So it's that's why it's per second. So we can cut off these two unit, second and per second. So this equation, the unit for energy is joule. Joule. Yeah. When you calculate this formula, the energy you get joule, hf also you get joule. You get SI unit. You get SI unit. You won't get another unit of energy, which is electron word, which we will learn about later. Yeah, electron word. This formula, you will first get the unit joule. Joule. Yeah, SI unit, because the h is already joule second, already joule. That's why the energy you calculate is joule. Yeah, energy for one photon, joule. Okay, energy for one photon depend on frequency and also depend on wavelength. That's why here it say energy of the radiation of the photon depends on frequency. So what is actually frequency? Some of you may ask, what is actually frequency? Energy of one photon depends on the frequency, or we can say frequency can be changed to wavelength. So it also depends on the wavelength of light, or radiation. Don't say light. It's actually the more appropriate terms is of radiation, of any electromagnetic radiation. It can be radio wave, can be X-ray. You know that energy for one photon. So it depends on frequency and wavelength of this radiation. So what is mean by this frequency and wavelength? Still remember about the wavelength? Let's talk about the wavelength. Wavelength is actually, we have wavelength of red light, which is 700 nanometer. We have wavelength of violet, which is 400 nanometer. So I better draw something here. This is red light lah. Red light, and this is Violet. I don't have a violet here. I want more colors. Violet, violet, give me a violet. This is the violet. Sorry. Where is my violet? So sorry, again. Now, where is my violet? I want my violet light. Yep, this one. This is the nice. Okay. Now, yeah, this is violet. See that? Red light wavelength 700, violet 400. Energy, the energy of photon, depends on what? Depends on the type of light. It depends on the type. Different wavelength, different type. Different wavelength, like 700 nanometer is red light. Violet is 400 nanometer. So different type of light, different type of radiation is So you see this is a very short. Violet is very short. Violet is very short wavelength. Red is very long wavelength. You see, red is very long wavelength. So red is very long wavelength. So the wavelength is this frequency and wavelength is the same lah. Yeah. We know that the higher the wavelength, the lower the frequency, isn't it? Like this one has a long wavelength but very low frequency. This one has a short wavelength but has very high frequency. So after that we have red. We have infrared. We have all those like that. We have infrared here. Yeah, infrared is category long wavelength. Infrared. We have radio. We have microwave. You see, and then violet. We have high frequency. Light. We have ultraviolet. Yeah, violet is like ultraviolet. Red is like infrared. Ultraviolet. We have X-ray. We have gamma ray. So energy of photon depend on the type. That's why I say it's the type. Yeah, wavelength or frequency is actually the type of radiation. Type of radiation. So energy of one photon, energy, it depends on the type of radiation. When we say energy depend on frequency or depend on wavelength, it means that energy depends on type of radiation. For example, like you see, like here, let's use the formula for Planck. What is the formula? E equal to hf, isn't it? Planck's quantum theory formula. E equal to hf. Like you see, energy. Just use the formula E equal to hf. E equal to hf. Okay. So you see this one. This one has a very low frequency. Very long wavelength. Low frequency, like you see this red light, infrared, radio, microwave, all of them have very low frequency but very long wavelength. Low frequency, long wavelength. Low frequency, low energy. So we can describe the particle like very small only. It carry amount very small amount of energy. Maybe energy of this is only 0. Energy of one photon. Energy for one photon. Energy for their one photon or one quantum. one photon or one quantum is maybe 0.00000. It's very less energy. But for high frequency, for like ultraviolet, gamma ray, X-ray, violet light, they have high frequency, they have high energy. So this type of light, this energy for one photon, this type of light has very big, big photon. Big photon means carry a lot of energy. Yeah, it carries a lot of energy. Maybe this energy is a lot. It's maybe 10,000. But this is just impossible lah. This is just you cannot have one photon with 10,000 joule of energy. This is too much. What I'm just trying to say is energy. This is just descriptive only. Energy for one photon. For one photon of X-ray, gamma ray has a lot of energy. But energy for one photon of radio wave, microwave, very little amount of energy. Okay, low frequency, low energy; high frequency, high energy. So, so again, I want to say is energy of one photon depends on the frequency or type or wavelength of light. Or we can say energy of one photon depends on the type of radiation we have. Is it a red light or is it a violet light? Is it a microwave or is it a X-ray? So different type of light, different type of radiation has different frequency and or different wavelength, and they have different energy for each photon they have. Yeah, so we can imagine like the radio wave light, the energy is like that lah. Very small photon, very small photon. Each of them has this amount of energy only. But for energy for the ultraviolet, gamma ray, they have all their photons like so much energy. Okay, this is like gamma ray. This gamma ray. This is like the radio wave or microwave. Okay, so okay, maybe energy depends on the type of radiation. I can show you here. I have one simulation for you to see. This is the one. You see that? Okay, you see, this is the one. So you have you see here, red light. Red light has you see 700. This is the red light. If violet is lambda equal to 400 nanometer, violet light. So different. See, yeah. So control frequency, control wavelength. So different frequency, different wavelength is different type of light. Different type of light means you have red, you have violet, you have orange, you have green, you have yellow. So different frequency or different wavelength means actually it's different type of light. Or different maybe microwave or radio wave or X-ray. Okay, I hope you are really clear about that. Now here the last one. So what is one electron volt? What is one electron volt? Electron volt means electron volt means is a unit of energy. A unit of energy that can be defined as the kinetic energy gained by an electron in being accelerated by a potential difference of voltage of 1 volt. That means it's the kinetic energy that gained by the electron after accelerated by potential difference of 1 volt. So 1 electron volt is 1.6 exponent negative 19 joule. Okay, let's look at this one. Yeah, look at this one. So this is what it means by the 1 electron volt. You see, I have you learn in the first chapter, yeah, electrostatic. Okay, you have 2 parallel plate, isn't it? And you have 1 electron. This is actually 1 electron charge. 1 electron charge. So this electron start from the negative plate. Okay, the potential difference between these 2 plates is 1 volt. The negative one is lower potential, positive is higher potential. So if the potential difference or voltage or potential difference between the two, this is the potential difference between the two plates is 1 volt. 1 volt means the negative is 0 volt, the positive terminal is 1 volt. This is the one electron charge. So we know that electron will be attracted to positive plate. Yeah, it'll be attracted to the, you got the electrostatic force attracted to the positive plate, isn't it? So since it got the force, so it will be accelerated, because we know that because of the Newton's second law, total F equal to ma, and this F is the electrostatic force causing the acceleration, isn't it? Is the electrostatic force causing the acceleration. So this electron will be accelerated. So once it accelerates, it will gain kinetic energy. How much kinetic energy it gain? After accelerate for 1 volt, 1 volt potential difference, how much? The answer is the kinetic energy it gained by this electron after accelerated by 1 volt potential difference, which is 1 volt means is 1 minus 0 lah. 1 volt means 1 minus 0, which is 1 volt. Okay, high potential minus low potential, right? So after being accelerated, how much kinetic energy gained by this one electron charge after accelerated by 1 volt potential difference? The kinetic energy it gets is 1 electron volt. 1 electron volt is 1.6 exponent negative 19 joule. Why it has this kinetic energy? Because when electron is near the negative plate, it has the potential energy U. So when it accelerates to the positive plate, actually it's changing from potential energy to kinetic energy. It's just conservation of energy. Potential energy convert to kinetic energy. Because this potential energy is actually like, we have the formula to calculate the potential energy, which is U equal to Q delta V, isn't it? This Q is the delta V. U is the Q delta V. So this Q is what's the energy? What's the charge for this electron? Electron charge, isn't it? What is the potential difference? Actually this is change of kinetic energy equal to change of potential energy. So the change of potential energy is actually charge times change of potential difference. The charge of the electron is E, and the potential difference between the two plates is 1 volt. 1 volt. So what is the value? It becomes 1 electron volt. Electron multiply 1 volt become 1 electron volt. And what is the what is the charge of 1 electron? What is the charge of 1 electron? 1 electron is 1.6 exponent negative 19 coulomb. Yeah. So again, maybe I rub again this one. So one electron multiply change to value. Electron is 1.6 exponent negative 19 multiply. Then you get joule. That's why the in unit joule is 1.6 exponent negative 19 joule. So 1 electron volt is actually 1.6 exponent negative 19 joule. Okay. So that 1 electron volt is this amount of joule lah. So we can so electron volt is actually energy unit. It's actually an energy unit when for this photon. This photon we can have 2 energy unit. This photon sometimes it is measured in terms of electron volt, sometimes in terms of joule. This photon energy, sometimes we put as electron volt, sometimes we put as joule. Yeah, electron. To calculate, to change the unit from electron volt to joule, we multiply multiply, we can say this is just like multiply the charge of the electron. Yeah, 1.6 exponent negative 19 joule. 19. If you want to change from joule to electron volt, we divide. The opposite is become divide lah. Divide. Okay. Back to electron volt. This is very important. Yeah. So let's say if I have energy for 1 photon, energy of the 1 photon is maybe energy for 1 photon, which is 1.33 electron volt. So I want to change to joule. How? I want to change to joule. How? 1.33 multiply we electron volt change to joule. Change to joule, we multiply. So we multiply 1.6 exponent negative 19 become joule already. Understand? Then you get the answer in joule. But if the question gives you energy for 1 photon, okay, I want to write if the question gives you energy for 1 photon is maybe 2.7 joule. I want to change to electron volt. How to change to electron volt? How to change to electron volt from joule to electron volt? From joule to electron volt, I divide 1.6. So I divide 1.6, so I will get so 2.7. I divide 1.6 exponent negative 19. Then the answer will be electron volt after divide. Okay, after divide. Okay, so that's all for the part 1 videos. Okay, see you in the next video. Okay, bye.